Assalamualaikum. It's me Isha and my presentation topic is comprehensive analysis of RDX Nanoenhanced energetic material. Today I'm taking you inside at one of the most exciting frontiers in material science, that how we are reinventing explosives at the nanoscale. We are going to explore how taking a 75-year-old workhorse explosive called RDX and engineering it at the scale of billions of a meter is creating materials that are smarter, more powerful, and more safer. My presentation is titled A Comprehensive Analysis of RDX Nanoenhanced Energetic Material. For decades, explosive research meant finding new molecules. Today, the breakthrough is nanoengineering, not making things smaller, but designing complete material architectures at the nano scale. We strategically incorporate nanoscale fuels and oxidizers to fundamentally control how and when energy releases. This report shows how we are transforming RDX by pairing it with two revolutionary partners like a nanoaluminium as a super fuel and nanothermites as explosive boosters. The goals are clear: more energy, precise control over that energy, and paradoxically improved safety. There are two basic concepts in this topic, that what is RDX. First, let's understand our base material RDX. Think of it as the high performance V8 engine of explosives. It's a white crystalline solid discovered before World War II. Its chemical name is a mouthful: cyclotrimethylene trinitramine. Here, what makes it special? That it detonates at an incredible 8,750 meters per second. That's over 19,000 miles per hour. It packs tremendous energy in a small space. But here's the problem, that RDX has what we call the power danger trade off. The more powerful it is, the more sensitive it becomes. So it's so touchy that in practice we have to mix it with wax or oils just to handle it safely, which waters down its maximum performance. The basic concept about nano enhancement, that what do we mean by nano enhancement? This is not just grinding RDX into finer powder. That's a common misconception. True nano enhancement means we are giving that V8 engine a complete upgrade. We are adding like turbochargers in the form of nano aluminum particles that burn hotter and longer, and other advanced fuel systems like nanothermites that provide explosive boost. Computer controls through designed architectures that program the energy release. The nanoscale materials, that's the 1 to 100 nanometers, about 1 to 100,000 the width of a human ear, gives us these three superpowers like a perfect mixing. At this scale, materials blend intimately like the fine dust filling every space in a room. And this in second space, we lightning fast reactions. The distances are so small that everything reacts almost instantly. And the next is defect elimination. Defect elimination, we can engineer out the microscopic flaws that make traditional explosive dangerous. Now we see that why do we need this nano approach. This is the performance safety dichotomy, the fundamental trade off that has plagued explosives for a century. On one axis, their energy, and on the other, safety. Traditional materials force us to choose: high energy means low safety, or good safety means reduced energy. These are two perspectives. But in RDX, it's in a difficult spot here. Great energy, but a problematic safety. The wax we add to make it safe enough to handle pushes it down the safety axis but also drags down its energy. Now watch this nano engineering breaks this trade off. By working at the nanoscale, we can push materials into new territory like high energy and high safety and improving its safety. We are not just moving along the old curve, we are creating a new one. And this report will dissect the science behind RDX nanoenhancement, focusing on the most powerful pathway, the integration of nanoaluminium and nanothermite composites to create a new class of architectured reactive material. Now we see the foundational science, the chemistry of RDX. What is RDX chemically? To appreciate the enhancement, we need to understand what we are enhancing. Here's the RDX molecule, that is a heterocycling ring structure known as triazine, where the three nitrogen atoms are each bonded to a nitro group. This structure is both oxygen rich and highly strained. This structure is perfect for rapid decomposition, but here's a crucial practical point that RDX crystals come in different forms called polymorphs. One form, the beta form, is significantly more sensitive. So controlling crystal structure during nanoprocessing is not just academic, it's critical for safety. Now we see how does it explode. It's a three-step process. The first is the detonation of RDX is a complex process that is initiated by a shock wave that drives ultra-fast chemical reaction. The mechanism occurs in stages like first is initial endothermic step, and it's also known as shock wave hit that providing energy to break the weakest link, the NO2 bond. The step actually consumes energy, so it consumes energy, so we call it an endothermic step. And in these intermediates form like a formaldehyde and nitrous oxide, and the formaldehyde and nitrous oxide intermediates are then oxidized in a series of highly exothermic reactions, and these reactions release energy that sustains the detonation wave. The final step produce hot gases like carbon monoxide, steam, and nitrogen. Remember, these gases, they become fuel for our nano enhancers. Now we see that how RDX made, the industrial synthesis of RDX. Before we look at nano enhancement, let's see how RDX is made industrially. This shows two historic processes. One is Woolwich process and the other is Bachmann process. The Woolwich process, also known as direct nitration, and the Bachmann process, also known as mixed acid nitration. The Woolwich process is the simpler and the older method. It takes hexamine and attacks it with concentrated nitric acid at very low temperature at almost 25 to 30 degrees centigrade. It works, but with modest yields around 70 to 80% and lots of waste. And in the other process, the Bachmann process, that's also known as mixed acid nitration, it's developed by American chemist Werner Bachmann, and its name is after the chemist. This process became the industrial standard due to its superior yield and efficiency. It's a combined acid method that nitrates HMTA, that stands for hexamethylene tetraamine. There is a unique cage-like tetrahedral structure using a mixture of nitric acid, ammonium nitrate, and acetic anhydride in an acetic acid solvent. And it's developed during World War II. and it runs warmer, is more efficient, and it gives yield over 85%. And why you show this? That because it illustrates a key theme. The practical application of RDX has always been tied to process innovation. In the 1940s, it was chemical engineering breakthroughs. Today, it's a material science breakthroughs at the nanoscale. As you see the structure of RDX that we see in the chemistry, like C3H6 and 6O6. See in the structure that there are three carbon atoms and three nitrogen atoms are attached with carbon atom, and the further three NO2 groups are attached with nitrogen groups. So the total number of nitrogen atoms are 6, and O2 O2 O2, the total number of oxygen atoms are 6. So N6 O6, and each carbon contains two hydrogen atoms to complete its valency, CH2. So the total number of hydrogens are also 6. So the molecular formula of RDX is C3, H6, N6 and O6. Next, we see that the Beckman process ability to utilize cheaper ammonium nitrates as a nitrating agent and its higher efficiency made it the cornerstone of large-scale RDX production for decades. Understanding these synthesis pathways is not merely of historical interest. It underscores the fact that the practical application of RDX has always been tied to advancements in a chemical process engineering, much like its current nano-enhancement is tied to advancements in material science. Next, the primary nano-enhancer, and also known as the star enhancer, nanoaluminium. Nanoaluminium is the most extensively studied and the applied metallic fuel for nano enhancement. Its properties are a direct consequence of its synthesis route. Now, this is not an aluminium fuel foil, it's a complete different material because of how we make it. Look at this comparison. The methods of formation of nanoaluminium, like the first is mechanical pulverization, in which we study ball milling. The ball milling method is also known as the top down method, and imagine taking some aluminium chunks and smashing them with nano sledgehammers. It's effective producing particles from 20 to 200 nanometer, but mainly gives a mix of sizes, and its aluminium content with active aluminium content around 87 to 0.44%. And low temperature ball milling can produce particles as small as 10 to 15 nanometers. Here is an image that shows us different areas. Like first is a throwing area. Throwing area, the section where grinding media are lifted and thrown by the rotating mill. And the next is the falling area, the zone where lifted balls cascade down onto the material below. And it's a primary size reduction zone where particles are fractured. And the next is impact area, the point where falling balls strike the material bed or mill liner, and it's a direct particle collision through high energy collisions. And the one is the milling area, the region where impact and grinding forces work on the material, like combined size reaction, continued size reduction through both impact and rubbing between ball particles and the mill walls. Inert area is also known as a dead zone, where minimal active grinding occur. Particles may settle here with less movement, and it affects overall milling efficiency, and engineers try to minimize this zone. And the last area is empty area, the space where balls are airborne before falling. And the next method is ultrasonic ablation. And it's an emerging technique where a titanium screw driven by ultrasonic waves physically scrubs aluminium foil into nanoparticles. This method is noted for being fast, green, and producing a narrow size distribution with high purity. The next method is about evaporation condensation methods. The first is laser induction composite heating. Like this method uses high frequency induction to pre-melt aluminium followed by laser to vaporize it. Like here we vaporize aluminium with a laser and let it condense into perfect spherical nanoparticles with 15 to 60 nanometers in size. We can even add methane to create a carbon coated nano aluminium by introducing methane into the chamber, creating a core shell structure that passivates the surface. And the next is arc and wire explosion methods. These methods use a high current arc or a powerful electrical pulse to explosively vaporize aluminium wire or rods. They are highly scalable and produce spherical high purity particles. The arc method yields particles of 20 to 100 nanometer with active aluminium up to 72 to 72.35%, while the wire explosion method typically produces particles of 50 to 90 nanometer. These are also known as bottom-up approach of producing nano aluminium particles. But the method you choose depends on what you need, like ball milling for cost-effective production and vaporization methods for purity and control. And the next is chemical synthesis method. It involves solution reduction. The bottom-up approach involves the chemical reduction of aluminium salts like aluminium trichloride by agents like lithium aluminium hydride in an organic solvent. Its principal advantage is exquisite control over particle size 20 to 120 nanometer. And the ability to form perfect core shell structure during synthesis by adding coating agents like oleamine and triphenyl phosphine. However, it's a complex, low yield and generates chemical waste, also making it primarily a laboratory scale technique. Now we study about a fundamental challenge that we face, the oxide shell and passivation. The moment nanoaluminium hits air, it instantly grows a 2 to 5 nanometer thick shell of aluminium oxide. Think of it as a nanosuit of armor. While this lets us handle the particles, it causes three big problems in their performance. Like the first is diffusion barrier problem. Like the aluminium trioxide shell acts as a physical barrier, preventing oxygen from reaching the core of aluminium metal and hindering its ignition and combustion. And the next problem is dead weight problem. That this oxide doesn't contribute to energy release. It just dilutes our formula. And the next is the aging problem, that over time, especially in humidity, this gel thickens, gradually loss of active aluminium content and also its reactivity decreases. This poses a significant challenge for the long-term storage and shell life on nano and aluminium enhanced formulation. This oxide shell is why 100 grams of nano aluminium doesn't give you 100 grams of energetic materials, you might only get 70 to 85 grams of actual fuel, and the rest is package. Now, we study about how we solve the shell problem, advanced nano aluminum coatings. So we engineer a better interface. We have two coating strategies. The one is passive protective coatings and the other is reactive energetic coatings. These coatings are designed to provide a superior barrier against oxidation compared to the native aluminum trioxide without actively participating in the energetic reaction. Like the first is polymer coating and the other is boron coatings. Polymer coatings like polystyrene, that's a polymer, thermoplastic polymer, long chains of styrene units, that's a synthetic polymer, and hydroxyl terminated polybutadiene toluene diisocyanate form a continuous physical barrier around the nano aluminium, and it shows that polystyrene coated nano aluminium retained an active aluminium content of 76.06% after 30 days of storage in air, whereas uncoated nano aluminium under the same condition saw its active content plummet to 42.3%. And the other is boron coating. This provides exceptional protection, and it's demonstrated that boron coated nanoaluminium stored in 70% humidity for 1 year saw its active aluminum content drop only marginally from 84% to 82%. The next we study reactive and energetic coatings. These coatings are engineered to react exothermally with nanoaluminium core or the surrounding environment, thereby enhancing the overall energy output and improving its ignition. Look at this reaction, that fluorine is a stronger oxidizer than oxygen, and the aluminium fluorine reaction is tremendously energetic. The data shows coating nanoaluminium with PTFE, which stands for polytetrafluoroethylene, rockets its heat output from 0.88 to 4.80 kilojoules per gram, a more than 5-fold increase. We also use energetic polymers like GAP, nitrocellulose, also to increase its reactivity. Like energetic polymers, these binders contribute their own chemical energy. Glycide azide polymer onto nanoaluminium, forming a chemical bond, and the resulting composite shows shorter ignition time and more intense flame. Nitrocellulose composites composites by electrostatic spraying, which reduce the ignition delay time dramatically from 14 millisecond to 0.3 millisecond, and it's produced a dazzling fire. So we see here that it's contribute their own energy and cut ignition times from milliseconds to the microseconds. Now we study about the synergistic partner molybdenum trioxide for nanothermites. While nanoaluminium enhances RDX through after burning, and its combination with nano oxidizer creates a distinct class of materials known as metastable intermolecular composites or nanothermites with molybdenum trioxide. By mixing nanoaluminium with nano oxidizer molybdenum trioxide, we create a metastable intermolecular composites. Let's look at this reaction. Here we see that two aluminium and molybdenum trioxide react and give us heat of about 4.2 kilojoule per gram. Now the question is, why molybdenum trioxide? There are any reason behind this? First, the reason is it's incredibly energetic. That at 4.8 kilojoules per gram, it's one of the hottest thermite systems. And the second is it's a gas generator. It's a unique characteristic of molybdenum trioxide that molybdenum trioxide sublimes. Sublimation means turns directly to gas around 700 degrees centigrade before fully reacting. This produces gaseous molybdenum trioxide species that permeate the material, enhancing pressure buildup and leading to a more violent explosive reaction rather than a simple combustion. This combustion of high heat and rapid gas release is ideal for enhancing blast effects. Here's the nano effect in action. Conventional thermites burn at about Conventional nanothermites burn at about 1 meter per second, but nanothermites they can propagate at over 1000 meters per second. And that's the power of nanoscale intimacy. And this highlights the profound impact of reduced diffusion distances. Next we study about advanced composite architectures and performance data. The true power of nanoenhancement is realized when these components are intelligently integrated with RDX. The first is Architecture 1 RDX plus nanoaluminium mechanical mixture. Here's a mechanism that RDX detonates first, then the nanoaluminium particles ignite in the hot fireballs and undergo after burning with the detonation gases. This after burning extends the pressure pulse. Instead of just a sharp bang, you get a bang followed by a sustained wash. The data confirms this, replacing just 5 to 10% of micron aluminium with nano aluminium in RDX formulations increased expansion work by 5.5 to 10.2% in cylinder test. For underwater explosive that's critical for naval applications, nano aluminium formulations showed higher total energy output. Next, Architecture 2, we study RDX plus nanothermite, nanoaluminium and molybdenum trioxide. That is a synergistic approach. This mechanism creates a dual stage or co-detonic material. That it's not a sequential, it's co-detonic. The shock and heat from RDX detonation provide the perfect instantaneous trigger for the ultra-fast nanothermite reaction. The energy is released simultaneously and amplifying each other. And the energy releases from a molecular explosive and nanocomposite occur almost simultaneously, leading to the synergistic boost. And what the performance implications in this case? Like it enhanced detonation heat, the substantial heat from the thermite reaction, so about 4.2 kilojoule per gram, adds directly to the total energy output. Superior Periblast is about the rapid gas generation from molybdenum trioxide sublimation and the violent thermite reaction amplify the peak pressure and impulse of the blast wave. And what's about the tunability? Tunable output means the ratio of RDX to nanothermite allows engineers to dial in the desired output from a sharp shock RDX dominated for penetration to sustained push, thermite dominated for blast effects. Like it means that by adjusting the RDX and the thermite ratio and want a sharp shock for armor penetration, use more RDX, want massive blasts for demolition, use more thermite. So this is a programmable energetics. And the next is core shell and the ordered structures. In this we study that moving beyond random mixtures to designed architectures, and examples include that we study before nano aluminum molybdenum trioxide core shell particles or RDX nanothermites particles created by the electrospray or vapor deposition. Benefit: maximizes fuel oxidizer intimacy, reduces ignition delays, and can be used to control reaction propagation. The next is quantifiable performance enhancements. The performance leaps are dramatic. The first is ignition. The minimum ignition energy for 35 nanometer nanoaluminium is less than 1 millijoules compared to 59.7 millijoule for 40 micrometer micro aluminium. So it's a huge difference. The next is detonation velocity. In RDX based explosives, VOD with nanoaluminium was higher than with microaluminium when aluminium contents was below 10%. The next is shock wave over pressure. In air explosion test, the peak over pressure for nanoaluminium containing samples was much higher at all distance that's compared to the traditional formulations and compared to microaluminium level samples. And the next is combustion in propellants. They're replacing microaluminium with nanoaluminium increased burning rates by 40% to 100% and reduced the amount of unbound metal in the residue. And this is not instrumental improvement, this is transformational improvement. Now we study about challenges that we face, future directions and conclusion about this topic. Of course, we face real challenges in making these RDX nano-enhanced. The first one is aging and long-term stability. The significant hurdles are aging and long-term stability. The interfaces between RDX, nanoaluminium and sensitive oxidizers like molybdenum trioxide are chemically active. Long-term compatibility, especially under varying temperature and humidity, is a major concern. For stockpile reliability. The other is processability. The high specific area of nanoparticles leads to extremely high viscosity in binder based formulation, making mixing, casting, and pressing difficult. But the new processing techniques such as solvent based slurry methods or additive manufacturing are required. The next is about sensitivity. While some nano enhancements can reduce impact sensitivity, the high electrostatic sensitivity of nano aluminum powders and the intimate fuel oxidizer contact in nanothermites can increase vulnerability to accidental electrostatic discharge. The next is cost and scalability. The industrial scale production of high quality coated with nanoaluminum and nanomolybdenum trioxide with consistent properties remains expensive compared to conventional materials. So it's a cost problem that we faced in these future challenges. We'll study about the future directions. The future of RDX nano enhancement lies in moving from a nano composite to designed energetic materials. The first is additive manufacturing. Now, what is additive manufacturing? Imagine making a cake where you mix everything into one batter and bake it. You get the same flavor in every bite, but the new way, that is 3D printing, is a new method. Now imagine printing a cake layer by layer, putting chocolate in some spots, vanilla in others, and caramel swirls in between. So every bite is different. So what this means for explosives, that instead of having a uniform block of explosive that goes bang all at once, we can 3D print an explosive charge with different materials in different places. So the outer layer is fast burning material for instant shock, middle layer slower burning material for sustained push, the special pattern spiral or grid patterns that control how the explosion spreads. So the real world example is about think of a smart warhead that can be programmed to first punch through armor, that is a sharp shock, then explode inside, there is a massive blast, all from the same charge because different parts are designed to react at different times. Now the other way is multi-scale modeling. Multi-scale modeling, the study as the old way is design a new explosive, make it in a lab, then test it, then fix problems, then test again. So it's an expensive, slow, and sometimes it's dangerous method. So the new way is computer simulation method, in which design on computer simulate how it will work, see virtual results, and then optimize design only make the best version of it. So it's a two-level computer modeling. Level 1 is molecular scale modeling, in which we simulate individual atoms and molecules, like watching a super slow motion movie of chemical bonds breaking during explosion, and then predict will this new coating make nanoaluminum ignite faster. And the answer is what happens at the nanoscale when RDX and nanoaluminum meet. And the second level is engineering scale, in which study about finite elemental analysis simulates the entire explosive device, like running a virtual crash test for explosives, and it can predict how will the blast wave spread. And the answer will be that will this casing contain the explosion properly. The real world example is, before ever touching real materials, scientists can design a new RDX nanoaluminum composite on their computer, then simulate its nanoscale reactions, then predict its full scale blast effects, that its finite element analysis, and then adjust the design virtually until it will be perfect. and only then make and test the real thing. And the next is now you see that why this matter. From one size fits all explosives, they do basically the same thing every time. So the programmable explosives that can be mission specific, that different designs for different targets, that would be predictable, we know exactly how they will perform before we make them. So it would be safer to develop, less trial and error, fewer failed tests, more efficient, and the most important thing is efficiency, that optimized material with no wasted energy. So old explosives were like firecrackers, light them and they go bang. Future explosives will be like smartphones, programmable, multifunctional, and precisely engineered for specific tasks. The next is bio inspired and green explosives. The old way is that we make explosive materials by mixing powders together and hoping that they will work well. It's like throwing different bricks into a box and shaking it, you get a random structure. But the new way that is a bio inspired way, we look at nature's design and the copying them. Some examples from nature, like nacre, mother of pearl. Now, if you see what it is, the shiny inside of seashells. Why it's amazing? Because made of brittle minerals, but arranged in a brick and mortar pattern. Its result is that it is incredibly strong and tough, that it doesn't crack easily. For explosives, could make material strong, but less likely to accidentally detonate. And the other is nature structure is bond structure. So what it is light but incredibly strong. It is porous inside, dense outside, but perfect strength to weight ratio. So for in case of explosives, it could make lighter charges that pack the same punch. Spider silk. What about it that it is stronger than steel but very flexible? So why it amazing that self assembles at room temperature? So in case of explosives, that it could create tough binder materials that hold explosives together safely. And self assembly, like nature's magic trick, instead of us forcing materials together like mixing cake batter, we design materials that automatically arrange themselves into perfect structures like crystals forming in a sugar water. Now we see the real world example in this case, that imagine designing nano aluminum particles that have special surface coatings. When we mix with it with RDX, they automatically line up in a perfect patterns, creating a material that's as organized as a honeycomb. And the result is more energy release and less chance for of accidental ignition. So in this bio-inspired and self-assembled structures, we see different examples, natural examples, to study for the nano-enhanced RDX, that mimicking natural structures to create materials that are both strong but less sensitive. And the other way is green energetics. Green energetics means environmental friendly explosives. The main problem is that explosives today contain toxic heavy metals like lead, mercury, chromium that poison the soil as well as water, and percolates like damage the thyroid glands, contaminate groundwater, and many other harmful chemicals that are dangerous for people and the environment. But the new way green energetics replace the bad stuff with safe alternatives. Like instead of lead based primers, use nano catalyst made from safe metals. Instead of perchlorate oxidizer, use organic or nitrogen based oxidizers, and instead of toxic binders, use biodegradable polymers. So it's nano magic for green explosives. That nano catalysts are the secret weapon. Tiny particles with huge surface area make reactions happen faster with less material, and it can replace pounds of toxic material with grams of safe nano materials. So in the real world example, see that the old shell is contains that is a toxic primer and leaves lead contamination in rainy grounds, and it poisons soil for decades. But the new thing is contains iron oxide nano catalyst, that is a safe primer. It leaves iron oxide, basically rust in the form of rust in soil, that biodegrades naturally, and there is no environmental damage because of this. Now we conclude this topic as the nano enhancement of RDX represents a mature and validated pathway to transcend the performance limits of traditional explosives. The extensive data confirms that nano aluminium, through advanced synthesis and coating technologies, dramatically improves the blast and thermal output of RDX formulations. And this integration of nanothermides like aluminium molybdenum trioxide enables synergistic energy release mechanisms we could only imagine a decade ago. While challenges remain in stability and processing, the path is clear. We are engineering a new generation of energetic materials that are not just more powerful but smarter, safer, and precisely tailored for 21st century mission. That's all about this topic.